This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion on the groundbreaking paper, Neural Turing Machines. This research proposes a novel architecture that combines neural networks with external memory, drawing inspiration from both biological memory and the architecture of digital computers. Our focus will be on the technical details and implications for the field. Let's start with the core concept. What problem does this architecture aim to solve?
The fundamental challenge addressed is the limitation of standard neural networks in handling algorithmic tasks requiring external memory and complex data manipulation. Recurrent neural networks, RNNs, while theoretically Turing-complete, struggle in practice with long-term dependencies and the efficient learning of complex procedures. Neural Turing machines, NTMs, aim to overcome this by providing a differentiable, trainable system that integrates external memory access.
The paper mentions the analogy to Turing machines and von Neumann architectures. Can you elaborate on the similarities and key differences in the context of this differentiable approach?
The similarity lies in the fundamental components: a controller, analogous to a CPU, and an external memory, like RAM. Both Turing machines and von Neumann architectures use explicit addressing to access memory locations. However, NTMs differ crucially by employing a blurry read-write mechanism, making the entire system differentiable. This differentiability is key, enabling efficient training via gradient descent, unlike traditional Turing machines.
This blurry mechanism sounds interesting. How does it work? And how does it ensure selective memory access despite its non-discrete nature?
The blurriness refers to the use of attentional mechanisms. Instead of directly addressing a single memory location, read and write heads generate weightings over all memory locations. These weightings, determined by the controller, create a focus, allowing the system to interact strongly with a small portion of memory while weakly interacting with the rest. This allows for selective access without sacrificing differentiability.
The paper describes content-based and location-based addressing. How do these mechanisms complement each other, and why is the combination crucial?
Content-based addressing allows retrieval based on the similarity between a key vector and memory contents, similar to hop-field networks. This is efficient for retrieving data based on its content. Location-based addressing, on the other hand, allows direct access to specific memory locations, crucial for tasks where data is addressed by location rather than content, such as arithmetic operations. The combination provides flexibility, allowing the controller to choose the most appropriate addressing method for a given task.
The choice of controller network, recurrent or feed-forward, seems significant. What are the trade-offs involved in using each type?
A recurrent controller, like LSTM, provides its own internal memory, complementing the external memory matrix. This allows for more complex computations and the retention of information across multiple time steps. A feed-forward controller, however, offers greater transparency, making it easier to interpret the network's operation. The choice depends on the complexity of the task and the desired level of interpretability.
The experiments cover several algorithmic tasks. Can you highlight the key findings and what they reveal about the NTM's capabilities?
The experiments demonstrate NTM's ability to learn and generalize simple algorithms like copying, sorting, and associative recall. In each case, NTM significantly outperformed standard LSTMs, showcasing its superior ability to handle long-term dependencies and complex data manipulations. The results suggest that NTMs can learn compact internal programs that generalize well beyond the training data.
The paper mentions the vanishing and exploding gradient problem, a common issue with RNNs. How does the NTM architecture mitigate this problem?
The NTM architecture mitigates the vanishing/exploding gradient problem indirectly through its memory mechanism. The ability to selectively store and retrieve information allows the network to maintain relevant information over extended time periods, reducing the reliance on long-term backpropagation through the controller network itself. The differentiable memory access ensures that gradients can flow effectively even for long sequences.
The addressing mechanism involves interpolation between content-based and location-based weightings. What is the purpose of this interpolation, and how does it contribute to the overall functionality?
The interpolation gate allows the NTM to smoothly transition between content-based and location-based addressing. This is crucial for tasks requiring a combination of both approaches. For instance, the controller might initially use content-based addressing to locate a relevant data region, then switch to location-based addressing to iterate through the region. The interpolation provides a flexible and adaptive way to manage memory access.
The sharpening mechanism, equation 9, is mentioned. What is its role in maintaining precision during long sequences?
The sharpening mechanism, controlled by the scalar got, amplifies the weights of the most prominent memory locations, effectively counteracting the potential for weight dispersion during iterative shifts. Without the sharpening, the attentional focus could become too diffuse over time, leading to reduced precision and accuracy, especially in long sequences. It ensures that the focus remains sharp even after multiple shifts.
The experiments with the copy task are particularly revealing. Can you describe the pseudocode algorithm the NTM seemed to learn and what it implies about its ability to learn higher level operations?
The NTM's solution to the copy task closely resembles a simple human-written program. Initialize a head to a starting location, write inputs sequentially, then return to the start and read sequentially. This demonstrates the NTM's ability to learn not just individual operations, but also sequential procedures, effectively creating and iterating through arrays. This suggests a capacity for higher level algorithmic thinking.
The repeat copy task adds a layer of complexity. How did the NTM handle the nested structure of this task, and what were the limitations observed?
The NTM extended its copy algorithm to handle the repeat copy task by repeating the sequential read operation multiple times, controlled by the repeat count input. While it successfully generalized to longer sequences, it struggled with accurately predicting the end marker when the number of repetitions exceeded the training range. This highlights a limitation in representing numerical values and their generalization beyond the training distribution.
The associative recall task introduces the concept of indirection. How did the NTM manage this more complex data structure, and what was the significance of the observed memory access pattern?
The NTM solved the associative recall task by writing compressed representations of items into memory using a combination of content-based lookup and location-based offsetting. The controller wrote a compressed representation of each item, including the limiters. Upon receiving a query, it recomputed the compressed representation, used content-based lookup to find the location, and shifted to access the subsequent item. This demonstrates the NTM's ability to handle indirect addressing and complex data relationships.
The dynamic n-gram task tested the NTM's ability to adapt to changing predictive distributions. How did it perform compared to the optimal estimator and LSTM, and what does this reveal about its learning capabilities?
The NTM demonstrated a small but significant performance advantage over LSTM in the dynamic n-gram task, though it didn't quite reach the optimal performance. Analysis of its memory usage revealed that it learned to maintain counts of ones and zeros for different contexts, effectively implementing a mechanism similar to the optimal Bayesian estimator. This highlights its ability to learn and adapt to dynamic statistical patterns.
The priority sort task is a significant challenge. How did the NTM approach this task, and what was the significance of the observed memory access pattern?
The NTM solved the priority sort task by using the priorities to determine the relative location of each write operation. A linear relationship was observed between the priorities and the write locations, indicating that the network learned to map priorities to memory locations. It then read from these locations in increasing order, effectively traversing the sorted sequence. This demonstrates its ability to learn and apply a complex sorting algorithm.
The paper compares NTMs with LSTMs across various tasks. What are the key differences in their performance and what accounts for these differences?
Across all tasks, NTMs consistently outperformed LSTMs, particularly in tasks requiring long-term dependencies and complex data manipulation. This is attributed to the NTM's external memory mechanism, which allows for more efficient storage and retrieval of information compared to LSTM's internal state. The external memory provides a more scalable and flexible way to handle complex data structures.
The paper mentions the use of ARMS prop for training. Why was this optimization algorithm chosen, and what are its advantages in this context?
ARMS prop was chosen for its effectiveness in handling non-stationary objectives and adapting to varying learning rates. Its adaptive learning rate mechanism is particularly beneficial in training complex neural networks like NTMs, where gradients can vary significantly across different parts of the network and over time. It helps to stabilize the training process and improve convergence.
Gradient clipping was also employed during training. What is the purpose of this technique, and how does it contribute to training stability?
Gradient clipping limits the magnitude of gradient components during backpropagation. This prevents excessively large gradients from destabilizing the training process, particularly in recurrent networks where gradients can accumulate over time. It helps to avoid exploding gradients and ensures that the training process remains stable, even with long sequences.
The paper provides detailed experimental settings, including the number of heads, controller size, and memory size. How are these parameters chosen, and how do they influence the NTM's performance?
The choice of these parameters involved experimentation and optimization. The number of heads influences the computational capacity, with more heads allowing for more complex parallel operations. Controller size affects the complexity of the learned programs, while memory size determines the amount of information that can be stored. The optimal values depend on the specific task and were determined empirically.
The paper concludes by highlighting the NTM's ability to learn simple algorithms and generalize beyond its training regime. What are the broader implications of this research for the field of artificial intelligence?
The NTM architecture represents a significant step towards building more powerful and flexible neural network models capable of handling complex algorithmic tasks. Its ability to learn and generalize algorithms has implications for various AI applications, including natural language processing, robotics, and symbolic reasoning. It opens up new avenues for research in differentiable computation and the integration of memory into neural networks.
This has been a very informative discussion on the intricacies of neural Turing machines. Thank you.